Okay, let's unpack this. Imagine a world where machines don't just hear sounds, but they listen, really listen, with an efficiency and, well, an intelligence inspired by our very own biology.
Mhm.
A world where your devices respond to you not just quickly, but, intimately, almost like another person in the room. Today, we're taking a deep dive into an incredible demonstration that really brings this future to life, showing us how our ears are literally shaping the next generation of smart technology, right at the very edge of our digital world.
And what's truly fascinating here, I think, is the elegant synergy of biology and, cutting-edge engineering. It's
Mhm.
quite something. We're going to explore a system that directly mimics the human inner ear for that initial audio processing bit, and then combines that bio-inspired efficiency with a highly optimized machine learning accelerator.
Right.
And all of this is running in real time on a surprisingly small, powerful chip. And the power consumption, it's minuscule. It's about making listening not just smart, but incredibly perceptive and crucially power efficient. It's pushing the boundaries of what's possible for truly intelligent edge devices.
Okay, so our mission for this deep dive is clear then. We're going to dissect exactly how this sophisticated system works, right from its fundamental bio-inspired beginnings in the human ear,
Hmm.
through its clever power-saving mechanisms, all the way to its real-time application in a surprisingly interactive demo. And then we'll peek at what this all means for the future of truly intelligent, always-on devices that understand us better than ever. Get ready to have your ears opened, both literally and figuratively.
Sounds like a plan.
So let's start at the very beginning, with perhaps one of the most incredible and honestly often underappreciated biological processors we know, the human ear. Think for a moment about how effortlessly your ear can pick out a single conversation in a bustling, noisy room. You know, that classic cocktail party effect,
Oh, yeah, absolutely.
where you can just filter out all that background chatter, music, clinking glasses, everything, just to focus on one voice. It's an incredible feat of natural, instantaneous processing, something we often take entirely for granted.
We really do.
The ability to not just register sound, but to differentiate, filter, localize, understand it, all while ignoring irrelevant noise. It's truly astounding.
It is. And it's a complex self-calibrating system, too.
Yeah.
It effortlessly handles this vast dynamic range, a multitude of frequencies, all in real time, all the time, with like no perceivable effort on our part.
Exactly.
And the core of that marvel, especially for that initial breakdown, the decomposition of complex sound frequencies, lies deep within the inner ear, specifically within a tiny snail-shaped organ called the cochlea.
The cochlea.
Inside this remarkable structure, you find two critical components working together, the basilar membrane and the inner hair cells. Now, the basilar membrane is a truly ingenious piece of biological engineering. It's essentially a long, thin strip inside the cochlea that varies subtly, but importantly, in stiffness and width along its length.
Okay.
When sound waves enter the ear, they cause fluid in the cochlea to vibrate, and these vibrations travel along this membrane. And here's the crucial bit. Different parts of the membrane resonate most strongly at different frequencies. The stiffer, narrower base responds to higher frequencies,
Mm-hmm.
while the wider, more flexible apex responds to lower frequencies. So it creates this natural, highly efficient frequency decomposition. It's physically separating the complex sound into its parts,
Wow.
like a real-time parallel frequency analysis happening right there in your ear before any significant neural processing even begins.
So it's almost like your ear has its own built-in, naturally tuned array of filters, each part of that membrane just instinctively responding to a specific frequency range.
Precisely.
It's automatically breaking down a complex sound wave into its individual components, almost like an acoustic prism, like you said, before your brain even gets deeply involved.
Exactly, like an acoustic prism.
And this is all happening in a purely analog way, a marvel of biomechanical engineering that predates any digital stuff. It's really a masterclass in efficient front-end signal processing from nature.
It really is. And that's where the inner hair cells come in to complete this first stage. These are specialized mechanoreceptors sitting right on top of the basilar membrane. As the membrane vibrates in response to those specific frequencies, these delicate hair cells get stimulated. They bend, and they convert those mechanical vibrations into electrical signals, action potentials, essentially.
Okay.
These electrical signals are then sent off via the auditory nerve to the brain for, further more sophisticated processing and interpretation. But what's crucial to understand here is the parallel processing and the inherent energy efficiency of this biological system. It doesn't analyze sounds sequentially, like one frequency after another. It processes a wide range of frequencies simultaneously, in parallel, with continuous, low-power, real-time analysis, providing this rich, detailed information to the brain, this kind of always-on, low-latency, low-power sensing. Well, it's exactly what engineers dream of achieving with artificial systems. But it's an incredibly tough challenge to replicate computationally.
And that dream, that pursuit of replicating nature's efficiency, brings us directly to the tech we're discussing today, the neuromorphic cochlea.
Here's where it gets really interesting. How do you actually build something that captures that kind of natural parallel processing efficiency,
Right.
which happens in an analog domain using, well, digital circuits?
Yeah, that's the challenge.
It's not just about recording sound, it's about processing it in a way that mimics how our own ears do it, right at the first possible stage,
Yeah.
to save power and improve accuracy later on.
And to mimic these auditory functions, researchers have developed what they call the neuromorphic cochlea. The core component of this, as they mention in their work, is something called the cascade of asymmetric resonators model, or R model.
Carmel.
Okay.
So now this isn't just a generic sound processing algorithm. It's specifically engineered to replicate the mechanical and electrical behavior of the basilar membrane and the inner hair cells.
Huh.
That asymmetric part of the name is quite key. It refers to how the resonators respond differently to rising versus falling frequencies, which closely mirrors the nonlinear sort of adaptive response of the biological cochlea.
Interesting.
This biological fidelity is what makes it so powerful. It often also includes things like a low-pass filter to further refine the signal, making the emulation even more accurate biologically and optimizing the signal for what comes next. And the output of this sophisticated CR model is then transformed into something called cochleograms.
Cochleograms. Right. What are those exactly?
Well, think of a cochleogram as a specialized visual representation of sound, but it's unlike anything you might be familiar with, like a standard spectrogram. While a spectrogram breaks down sound into frequency and time, often with a linear or maybe a purely logarithmic scale, a cochleogram is designed to highlight features much closer to how the human ear would process them. It visually represents the activity across different frequency channels, just as different parts of the basilar membrane would respond. It emphasizes transient changes and unique temporal characteristics, things vital for speech recognition. This makes it an ideal feature extractor because the information it provides is already pre-processed and organized in a biologically meaningful way, which makes subsequent machine learning tasks significantly more efficient, less computationally expensive.
So, what does this all mean for making machines understand what they hear, not just record it?
Well, we said instead of giving a computer just raw, undifferentiated audio data and forcing it to figure out what's important through, sheer computational power, we're giving it a kind of pre-digested version of the sound. The data is already filtered, structured, prioritized in a way that, well, billions of years of biological evolution has proven to be incredibly effective.
Right. That makes sense.
And to give you an idea of the impact,
Yeah.
a traditional processor might burn hundreds of milliwatts, maybe even watts, just doing basic audio filtering and feature extraction on raw audio.
Wow.
This bio-inspired approach, by filtering up front and in parallel, can slash that power demand for these initial stages, often bringing it down to just a few tens of milliwatts, maybe even less.
That's a huge difference.
It is. It's like replacing a supercomputer with, a pocket calculator for that initial crucial sorting task.
Yeah.
It's truly remarkable how nature provides this perfect blueprint for incredibly efficient and effective sound sensing right at the edge of the system, before any heavy-duty AI even kicks in.
So this biomimicry is really the foundation, the key piece for making smart devices truly smart and, crucially, energy efficient.
Exactly. It's the cornerstone.
That's a fantastic power-optimized foundation. Now let's talk about a really pervasive problem in the world of smart devices and, frankly, our daily lives. The challenge of always-on listening. You know how your phone or your smart home device is always listening for its wake word, right? Hey, Siri, or Alexa, or okay, Google. But that constant vigilant listening, it can be a huge battery drain, sometimes leaving your phone dead by midday or requiring your smart speaker to be constantly plugged into the wall.
Absolutely.
It's this fundamental tension between responsiveness, we want our devices ready the instant we speak, and power consumption. We want them to last all day or even longer without needing a charge.
Precisely. And this continuous full-scale audio processing, where the device is constantly running complex, high-power algorithms just to spot a wake word or maybe specific sounds, well, it comes with significant computational overhead. And energy consumption.
Right.
Imagine a large language model or even a smaller deep neural network running constantly just listening for Alexa. That requires a lot of processing cycles, a lot of memory access. And this is especially problematic for what we call edge devices, these small, often battery-powered gadgets meant to operate on minimal power far from the cloud or a power outlet.
Yeah, like wearables or sensors.
Exactly. If these devices had to run a high-power inference engine constantly, their battery life would be, frankly, abysmal, or they'd need impractically large, expensive power sources. So preventing that unnecessary power usage without compromising responsiveness isn't just a critical design challenge. It's really the design challenge for ubiquitous AI.
And this is where the ingenious solution implemented in the system comes in.
Yeah.
A wake-up module. It's designed to be that first line of defense, right? A super low-power gatekeeper that intelligently decides when the main, more power-hungry processing unit actually needs to get involved.
Mm-hmm.
It's about being smart about when to listen intently, only powering up the big guns when something truly important like your voice is detected.
That's precisely right. And the specific implementation here is a support vector machine-based wake-up module.
An
SVM. And its role is absolutely crucial for power efficiency. It acts as a highly selective gatekeeper. It only activates the main Raman tiny ML accelerator, that's the main inference engine, when a human voice is detected, which means Raman stays idle, essentially in a deep sleep mode, for the vast majority of the time, saving significant power.
Makes sense.
SVMs themselves are mathematically elegant and computationally quite lightweight algorithms. They're excellent at defining clear boundaries between different classes of data, in this case between, say, ambient noise and human speech. They're pretty much perfect for this always-on but ultra-low power filtering task.
And what makes it so efficient? Is it just the SVM itself?
Well, what makes this SVM wake-up module particularly efficient is its direct integration with the neuromorphic cochlea we just talked about. The CRR models output those specialized cochleograms, which already highlight biologically relevant features of sound, serves directly as the input features for the SVM classification.
Ah, I see. So it doesn't need to do extra work.
Exactly. There's no need for a separate, resource-intensive feature extraction stage just for the wake-up module itself. The data coming straight from our bio-inspired ear model is already perfectly suited, pre-digested, you could say, for the SVM to quickly and efficiently determine if it's hearing a voice. This tight coupling makes the wake-up module incredibly compact and computationally efficient. It consumes very little power while still being highly accurate and responsive.
Right.
It avoids needing, say, a complex neural network just for that initial wake word detection, which would definitely consume significantly more power.
It's like having that highly specialized doorman we mentioned, but maybe even smarter. It's a doorman whose only job is, can this guest speak?
I laughed slightly. Yeah, something like that.
And because the guests are already wearing these bio-inspired badges, the cochleograms, he doesn't need to do complex ID checks. He just glances at the badge and knows instantly if the main party, Roman, needs to be woken up.
That's a good analogy.
This proactive, intelligent power management, it really feels like a game changer for always-on devices, meaning they can stay alert for days or weeks, maybe, not just hours.
And the results from this demonstration really underscore this game-changing efficiency.
Mm.
The total power consumption of the entire design, including the neuromorphic cochlea, the SVM wake-up module, and the Raman accelerator, is just 98.21 milliwatts, operating at a clock frequency of 40 milliwatts.
98 milliwatts. Okay, how low is that, really?
Well, to break that down, 46.65 milliwatt is static power, just the power the chip uses being on. And 51.57 milliwatt is dynamic power, used during active processing. To put that in perspective, a typical little LED indicator light might consume 10, maybe 20 milliwatts. A smartphone just sitting idle can consume hundreds of milliwatts.
Okay.
So for a sophisticated real-time audio inference system capable of detecting and processing human voice with this kind of intelligence, under 100 milliwatts is remarkably low.
That is impressive.
It really raises an important question, though. How do they achieve such a low-power footprint while still ensuring a rapid and accurate response when voice is detected? And the answer lies not just in that bio-inspired front end, but also in the careful architectural choices and, well, extreme optimizations made for the main processing unit itself.
Okay, so that's truly an incredible achievement in power efficiency. We've got this bio-inspired ear doing the pre-processing check. We've got a smart power-saving system waking up the main intelligence only when it hears a voice. check. But what is that main intelligence? What's the brain of this operation that actually decodes these specialized cochleograms and makes the predictions about what's being said?
Right. That brings us to the Raman Tiny ML Accelerator, which is referenced in their work. Raman, as its full title indicates, is a reconfigurable and sparse Tiny ML accelerator.
Okay, tiny ML, remind us what that signifies.
Sure. Tiny ML itself signifies this fascinating and rapidly growing field. It's machine learning specifically optimized for resource-constrained edge devices. This means it allows complex AI tasks that traditionally needed powerful cloud servers to run directly on small, low-power hardware, right where the data is collected, often within milliseconds.
Got it. Edge AI.
Exactly. In this system, Raman's specific and crucial function is audio inference. It takes those carefully constructed cochleograms from the neuromorphic cochlea and essentially decodes the cochlear output to generate predictions. It's the engine that interprets these biologically inspired features and translates them into actionable insights, like identifying a specific keyword that was spoken.
And you mentioned its full title hints at its capabilities, reconfigurable and sparse.
Yes, those terms hint at why it's so efficient for edge devices.
Mhm.
When we say reconfigurable, imagine a chameleon that can change its internal organs, not just its skin, to perfectly adapt. Raman can quickly adapt its internal processing units to efficiently execute different types of neural networks, or even switch between different audio tasks, maybe from recognizing a wake word to classifying background noise, all without needing new hardware. It's very flexible.
Like sparse.
Sparse refers to its clever way of handling neural networks. Think of a huge network of roads in a city, but only a few are actually carrying traffic at any given moment.
Okay, yeah.
A sparse neural network, and by extension Raman, intelligently ignores those empty roads, the connections between artificial neurons carrying zero or near zero information. It focuses computational power only where data is actually flowing. This dramatically cuts down the number of calculations needed, reduces memory accesses, which translates directly into huge power savings, faster execution, and a smaller hardware footprint. All absolutely critical for tiny ML applications.
Okay, so we have this incredibly optimized brain, Raman, designed specifically for low-power edge AI using these clever, reconfigurable, and sparse techniques. But where does all this sophisticated processing actually happen? We're talking about real-time custom hardware, right? Not just a standard computer chip. Why use an FPGA for something like this instead of, say, a more traditional processor like a CPU or even a small GPU? What's the advantage there?
That's a great question. The hardware platform is absolutely critical for achieving this level of performance and efficiency. And it's a key reason why FPGAs are often chosen for these kinds of specialized applications. In this demonstration, all this processing happens on an FPGA, specifically the Ethernet Ti-60 FPGA.
FPGA Field Programmable Gate Array.
Yes, exactly. FPGAs offer significant advantages here. Unlike general-purpose processors, which have fixed architectures, FPGAs allow for completely custom hardware designs. You can literally configure the logic gates and the connections between them to create a circuit that is perfectly optimized for your specific task. In this case, the car model's parallel processing and the Raman accelerator's sparse computations.
So you're building the chip for the job.
Pretty much. This deep customizability means you can achieve superior real-time processing capabilities and far greater energy efficiency compared to trying to run these specialized parallel algorithms on a general-purpose CPU. Or even a GPU, which might just be overkill and less power efficient for this particular job. It's really hardware-software co-design at its best. You're building a custom digital circuit for the job every time you program it.
And what about the specifics? How much of the FPGA does it use?
Diving into the technical specifics, the entire design operates at a peak frequency of 75 MHz, which is quite respectable for an embedded system focused mainly on power efficiency and low latency, not just raw speed. In terms of resource utilization on that FPGA, it uses 38.5K 4-input lookup tables, LUTs, and 10.3K flip-flops.
LUTs and FFs.
LUT and
FFs.
Exactly. For those unfamiliar, LUTs are like tiny memory blocks that can implement any logic function, 80 gates or gates, more complex stuff. FS are memory elements that store a single bit of information, crucial for holding states and sequential logic. Now, to put those numbers in perspective, while a big high-performance FPGA might have hundreds of thousands or even millions of these elements, using only around 38,000 LUTs and 10,000 FFs for such a sophisticated audio processing and AI system is remarkably lean.
So they were very efficient with the design.
Extremely. It means they've designed the custom hardware with incredible precision, shedding any unnecessary logic. Like a finely tuned race car stripped down to just its essentials. These components are mapped as what Efinix calls exchangeable logic and routing XLR cells on their FPGA. That's their specific architecture for these versatile logic units. It just showcases how efficiently the specialized logic is integrated onto the chip. This level of optimization ensures the system uses only the bare minimum of resources required, which further contributes to its incredibly low power consumption and small physical footprint.
That's a really deep dive into the hardware. Okay, now let's walk the listener through the complete audio inference pipeline. Let's put all these pieces together, trace the journey from sound to command. So the journey of a keyword spoken by the user starts with the microphone sampling that sound at 16 kilohertz. That's 16,000 samples every second, capturing quite a bit of detail. This raw audio is then fed into the FPGA through something called the I2S interface.
Right, inner IC sound. It's the standard way chips talk audio. Ensures precise timing.
Okay. And this module combines the raw data into clean 16-bit audio samples. Once inside the FPGA, the Carr model, our neuromorphic cochlea, processes these audio inputs to generate those specialized cochleograms we talked about.
Right.
These are then subsequently provided directly to Roman for the actual inference step. It's a beautifully integrated, incredibly fast flow, isn't it? Designed from the ground up for speed and efficiency.
It really is. It's a testament to taking a complex multi-stage process and making it run smoothly on minimal hardware.
So how does the result get out?
Right. To complete that chain, the resulting keyword predictions that Raman generates, let's say it identifies left or right, are then transmitted to a host PC. This communication happens using an Arduino Nano, which acts as a kind of intermediary via the UART interface.
UART, like a serial port.
Exactly. Universal Asynchronous Receiver Transmitter. It's a robust and very common serial communication standard, like a dedicated phone line, basically, for the FPGA to reliably send its results to the PC.
Yeah.
So if we connect this to the bigger picture, what we're seeing is a fully integrated, incredibly low latency pathway from a sound wave hitting the microphone through bio-inspired pre-processing and efficient AI inference on custom hardware, all the way to an actionable command delivered to a computer.
It's a complete end-to-end demonstration.
It is, and it's a testament to how advanced AI can be miniaturized and made incredibly responsive, really bridging that gap between biological inspiration and practical application.
This all sounds incredibly sophisticated, and the technical details are fascinating, for sure. But what does it actually do in a tangible way? You mentioned this isn't just theoretical research stuck in a lab. They made a game out of it.
Chuckles. They did.
It's all about a fundamental task on keyword spotting, which you find in so many interactive devices we use daily. Imagine just directly controlling a digital experience with only your voice.
Indeed. Keyword spotting is exactly that. The ability of a system to reliably detect specific, predefined words or phrases spoken by a user. Think of saying Alexa, or Hey Google, or Siri.
Right, the wake words.
Exactly. It's a foundational task in voice control, hands-free interaction, human-computer interfaces. And the demonstration they built provides this tangible, real-time application of that capability. It makes these abstract technical achievements immediately understandable and interactive for anyone who experiences it. It turns complex algorithms into, well, a fun, engaging experience.
So let's set the scene for this live demonstration. Imagine you're standing there in front of the setup. As they show in their figure 1, you've got a host PC right in front of you, running the maze game and some visualization software. Then there's a microphone position, clearly just waiting for your voice. Off to the side, you see that compact FPGA board, that Efinix Ti-60 we discussed. And all these bits are neatly connected by an Arduino Nano 33 BLE, acting as the communication bridge between the FPGA and the PC.
Yeah, it's a compact setup. Looks deceptively simple, maybe, for the sophisticated processing happening inside.
Definitely. So how does the data flow in the demo itself?
Right. The data flow is key to its real-time feel and how seamless it is. When you speak into the microphone, it captures the sound, obviously, and transmits that audio data to the FPGA bit by bit in a continuous stream. The I2S module inside the FPGA takes this raw data, combines it into those precise 16-bit audio samples, which are then fed straight to the Carr model, our neuromorphic cochlea.
Okay.
The output from the Carr model, those unique cochleograms, is then passed to Raman, the tiny ML accelerator, for its inference to figure out the keyword. And importantly, both the raw audio, the processed cochleograms, and Raman's final predictions are continuously transferred to the host PC via that Arduino Nano. This allows for that real-time monitoring and control you see on screen.
And there's visual feedback too, right? You don't just speak and hope.
Yes, exactly. A key aspect that really enhances the experience and makes the invisible visible is the cochleogram visualization, running live on the PC. As you speak, you can actually see a real-time dynamic visual representation of how your words are being processed by the neuromorphic cochlea. You see the intricate patterns, the peaks, the valleys that your voice creates as this artificial basilar membrane vibrates.
That's cool.
It makes the whole abstract process of biological sound decomposition tangible. You witness the patterns your speech generates, patterns that Roman then learns to recognize incredibly accurately. It's like a direct window into the machine's hearing and understanding.
And what makes this demo so captivating for someone experiencing it isn't just seeing the processing right. It's that truly unique experience of immediate intuitive feedback and direct control. It's not just tech for tech's sake, it's interactive.
Absolutely. Visitors can see the live updates on the detected keywords, for instance, if they say left or right to navigate the maze. And they can also observe Roman's status. Is it active, inferring, or inactive waiting?
Ah, so you see when it's working.
Precisely. This transparency is crucial. It builds trust and understanding in how the system actually works. It's clear when it's just listening versus actively inferring a command. Then, the detected keywords are immediately encoded by the maze game application to trigger actions altering the game's direction, pausing, resuming gameplay. Your voice directly controls the on-screen action. It creates a truly hands-free and immersive experience.
And all this info, the keywords, the game status, your progress, it's displayed clearly, right? On a
Yeah.
sidebar or something.
Yes, exactly. This information is displayed on the application sidebar. It allows users to monitor their game progress and the system status in real time. It makes the interaction intuitive, responsive, easy to follow. You're not left guessing, you're fully engaged.
So you really feel in control.
To reinforce the overall impact, just imagine the visitor's experience. They witness this real-time demo of the neuromorphic cochlea mimicking the basilar membrane, visualizing the cochleogram of their spoken keyword. Simultaneously, they see the Raman TinyML accelerator decoding that complex cochlear output to generate precise predictions that directly control a game, right there on a PC through a GUI. What's truly fascinating here is how seamlessly this complex, bio-inspired processing translates into immediate, intuitive, and highly responsive control. It demonstrates a very practical, very engaging application of cutting-edge AI at the edge. It's a powerful statement about the future of human-computer interaction.
Okay, so we've broken down the ear, the chip, and the game. We've seen how biology inspires silicon, how clever engineering turns that inspiration into real-time, low-power intelligence. Now, what does this all mean for us beyond playing a admittedly very cool maze game? What are the big, impactful takeaways from this deep dive into bio-inspired audio inference and TinyML?
Well, I think the core achievement here is the successful development and demonstration of a sophisticated, real-time audio classifier that operates within incredibly tight power constraints. It's not just a theoretical concept, it's a fully operational system showing what's possible now.
Right.
The researchers have showcased the effective use of that 30 teraR section cochlear model for incredibly efficient pre-processing. So they built a highly detailed yet compact artificial ear that drastically reduces the data burden right at the start. This, combined with the inference engine Roman running in real time on an FPGA platform, represents a significant step forward for edge AI. And the entire design is extensively optimized, leading to that remarkable low power number we keep mentioning, just 98.21 milliwatt at 40 megahertz. These aren't just technical feats, they fundamentally shift what's possible at the edge, moving AI from the cloud into our everyday devices with unprecedented efficiency.
And connecting that to the bigger picture.
Connecting these achievements to the broader context. This work is a prime example of the transformative power of TinyML, edge AI, and energy-efficient computing. It demonstrates how advanced AI, capable of complex tasks like audio classification and keyword spotting, can be made to operate on small, power-constrained devices, right where the data is collected.
Which has huge benefits.
Huge benefits. It significantly reduces latency. No more waiting for data to travel to a distant cloud server and back. It dramatically enhances privacy by keeping sensitive audio data local to your device. Your private conversations don't need to leave the device unless you explicitly say so.
That's a big one for people.
It really is. And it makes intelligent devices truly ubiquitous, able to run for extended periods without constant cloud connectivity or frequent recharging. So this raises an important question, I think. How does pushing advanced AI to the edge fundamentally change our interaction with technology? Moving it from reactive, where we wait for a response, to truly proactive, personalized, maybe even predictive.
Meaning our devices can anticipate our needs?
Potentially. Understand context better, interact with us in a far more natural, less intrusive way.
That's a profound thought. And for you, our listener, imagine the direct impact this could have on the devices you use every day, potentially transforming them into more capable and, well, less demanding companions. We're talking about a future where your smart speaker isn't just listening more efficiently, but processing your request faster, with far less drain on its power, giving you more battery life, instant responses.
Precisely. The potential applications unlocked by such efficient real-time keyword spotting and audio classification are truly vast, compelling. Think of the next generation of voice assistants, far more responsive, always on without killing the battery, maybe capable of understanding more complex commands, more nuanced speech.
Yeah.
Imagine highly responsive smart home devices that don't need to be plugged in all the time,
Mm.
capable of local intelligence, maybe activating lights based on sound cues, or even performing predictive maintenance by listening to the subtle hum of an appliance before it fails.
Interesting.
Or consider assistive technologies for individuals with disabilities, where immediate local voice commands are absolutely critical for independent living, for personal safety, often in places without reliable internet.
That's a really important application area.
It is. Even in industrial monitoring systems, detecting specific sounds, like a failing motor bearing or a leaky pipe, could signal equipment malfunctions with unprecedented speed and incredibly low power, preventing costly downtime. All these applications benefit immensely from a system that operates with minimal power and maximum responsiveness. It fundamentally changes how we interact with and rely on our technology by making it truly personal and always available.
It's also just an elegant and you could argue a profoundly sustainable way to approach complex technical challenges, drawing inspiration directly from billions of years of biological evolution.
That's a great point.
This biomimicry isn't just about achieving incredible efficiency, it's about leading to more natural, more intuitive human-computer interaction, because the machines are perceiving the world in a way that sort of resonates with our own biological mechanisms.
It feels less like talking to a machine and maybe more like a natural exchange.
And if you thought advanced audio processing inspired by biology was cool, well, the researchers aren't stopping there. They're already looking to the next frontier, pushing the boundaries even further.
Ooh, what's next?
The explicit future scope mentioned in their work is the seamless integration of audio and vision modalities within the same system, expanding the application scope.
Audio and vision. Together.
Right.
Wow.
Yes, that's a significant leap. Currently, we're seeing advanced audio intelligence here. The next step is to combine that with visual intelligence on the same efficient, low-power platform. Think about the challenges of making a tiny device not only hear, but also see, and then process both streams of information simultaneously, efficiently. This isn't just stacking technologies, it's about creating a truly multisensory AI that mirrors how we humans perceive and understand the world.
Right, using multiple senses. If we connect this to the bigger picture, this is a fundamental step towards machines that can perceive and interpret their environment with a richness that more closely resembles our own. Imagine a device that not only hears your voice, but also sees your gestures, maybe reads your facial expressions, understands the visual context of your environment, processing both streams in real time.
That opens up so many possibilities.
It leads to entirely new forms of intelligent interaction, where devices understand context, nuance, intent in ways that are currently only really possible through human-to-human communication. It's about building truly multimodal AI that can understand our world perhaps as comprehensively as we do, paving the way for truly intelligent, context-aware companions.
We've taken a truly deep dive into an inspiring piece of technology today, witnessing how the intricate, energy-efficient design of our own ears is serving as a blueprint for smarter, more energy-efficient AI. From the neuromorphic cochlea translating sound into those bio-inspired cochleograms, to the smart SVM wake-up module, the powerful yet lean Raman accelerator decoding those features, and its real-time control of that maze game. We've really seen the very near future of intelligent systems at the edge.
Simultaneously, much like we do, and to process that information with such incredible efficiency on a tiny power-constrained device. What new forms of interaction, understanding, or maybe even creativity could emerge when devices can perceive the world in such a rich, multisensory way, deeply informed by biological principles, and react with split-second accuracy?
A truly fascinating thought to mull over until our next deep dive. Thanks for joining us on this journey of discovery.